Hello everyone, welcome to our discussion on the topic electric field and electric forces. So we have started this topic last session, but this time for the sake of those who are not able to attend our lecture, then I will repeat it and record this lesson so that you can review anytime you want. Okay? So these are the learning objectives or the learning outcomes that we want to achieve in this lecture. First, explain the process of charging, solve problems involving transfer of charge from one object to another, state and explain Coulomb's law, define and explain electric field, and solve problems involving electric field and electric force calculations. And then at the end, we will discuss the brief of Gauss law. All right, so why it's important to learn this electric field class? So the reason is that in wireless communications, so we know that we send the information via free space or in a vacuum environment. Okay, so it's very important to learn the concept, no, how this signal or signals are propagated through the air. Okay, so these are the basic concepts. So here's the origin of electricity. So if we can still remember, we have what we call electrons, protons, and neutrons. So from our illustrations here, so we have here the electron, that is the negative sign here. The positive sign here represent protons, and we have here there's no sign. It means they are neutral, or we call it neutron. So the electrical nature of matter is inherent in atomic structure. So we have here the mass of the proton equal to 1.673 times 10 to the minus 27 kilograms, and for the neutron, the mass of neutron is 1.675 times 10 to the minus 27 kilograms, and mass of electron is equal to 9.11 times 10 to the minus 31 kilogram. And in terms of charge, so electron has a charge of 1.60 times 10 to the minus 19. C here stands for coulombs. Okay? So in nature, atoms are normally found with equal numbers of protons and electrons. So they are electrically neutral. By adding or removing electrons from matter, it will acquire a net electric charge with magnitude equal to E, that is the electrons, times the number of electrons added or removed, call it N. All right, so the charge is equal to N times E. All right, so this is our basic formula class that we need to remember. We will be using this in our succeeding discussions. Okay, so remember this. So this is the result of by adding or removing electrons from matter. It will acquire a net electric charge with a magnitude equal to E times the number of electrons added or removed. So N times E. Okay, so this is the charge, the electric charge Q. The product of the number of electrons removed or added and multiplied by E. So we know the charge for E, this one. Okay. So for example, a lot of electrons. So how many electrons are there in one coulomb of negative charge? So from this formula, charge Q equal to N times E. Okay, so from this, so solve for n, we'll divide both sides by E, right? And we have here, so we have one coulomb. So we're given the problem one coulomb. So one coulomb. So E is as given in the previous slide, 1.60 times 10 to the minus 19 coulomb. So we got here 6.25 times 10 to the 18. So these are the number of electrons in one coulomb of negative charge. Okay, so this is the number of electrons. So we're asked here how many electrons. Okay, so this is the number of electrons. And all right, so I hope you understand this basic concept class. Again, we will be using this in our succeeding discussions. And we have what we call electrostatics. So electrostatics is the branch of science that deals with the phenomena arising from stationary or slowly moving electric charges. Then we have what we call charging by friction. So friction meaning rubbing. As two objects rub together, the resulting heat energy may cause one object to lose electrons and the other object to gain electrons. So you can try to rub your hands. Rubbing your hand, what you will feel is that there will be heat produced. Okay, so you can produce heat, and by doing so, there will be perhaps in your left hand it loses electron, and on the other hand it gains the electron. So we have charging by contact. So here a while ago we have charging by friction, now charging by contact. By contact, when you take a neutral object and touch it with a charged object, and when a charged object touches a neutral object, there can be, okay, so this, sorry, because this should be, there can be. So there can be a transfer of charge from one to another. Then the neutral object becomes either positively or negatively charged. Think of it as a healthy person being touched by a sick person, and the disease or illness is contagious by touch, and you have the transfer of the disease from one person to another. So that is an analogy of charging by contact. Okay, so an illustration here, we have charging by induction. So we have to induce, and then charging will happen. Charging an object without direct contact. So that is what we call charging by induction. Okay, so here's an illustration here. We have an animal 4. Okay, then we have here an ebonite rod. So assuming this is positively charged, and this is the rod, ebonite rod is negatively charged. So it is possible to transfer electric charge from one object to another. So the body that loses electrons has an excess of positive charge, while the body that gains electrons has an excess of negative charge. Okay, so we have here the law of conservation of electric charge. During any process, the net electric charge of an isolated system remains constant. So it means the charge is conserved. It neither loss nor gain. So during any process, the net electric charge of an isolated system remains constant. So there will be no loss or no gain. So remain constant. Then we have like charges repel and unlike charges attract each other. So this is a very long time concept that you have learned. No, I think since elementary, I had learned this concept class, and I hope that you still remember it. So, assuming you have a charged object hung, no? Hung on the wall, for example, and then tied on a cord. So you see here the scenario when we have two opposite charges. So you see if they are hung on the for example the ceiling, all right. So you see that they will attract each other. So you can see the inclination of this cord. So they tend to touch each other. Okay, so this is an example of uh, charges opposite, unlike, no, unlike charges. So unlike charges attract, so they attract each other. But for like charges, like for example negative and negative, so like charges repel. Like charges repel. And so do with this one, plus plus positive charge repel. So it's like now in human beings. So if you have a girl attracts boy, boy attract girls, except for there's a new or another scenario, which I think you understand what I mean. So charged object and electric force. So we have here the base layer. We have here the microcapsules. Okay, so these are the beds. Okay, so dark liquid. So for example, we have here positively charged. We have a negatively charged. Or you can compare it with, so this one here. This represents this part, the blue color, and the light pixel here, or the white. Okay, so this is the positive, this is the negative. So this is just an illustration class of um, a charged object represented by this figure. Okay, so another way of explaining about these charges, positive and negatively charged or positively charged, is something like this class. No? For when we talk of conductors and insulators. So the analogy is something like this. We have here a hotter object, and we have here a colder object. So the heat normally transfer from hot to colder object. Okay, so in similar manner, we have here a negatively charged object, and we have here a positively charged object. So what will happen is that the negatively charged object will be attracted, or will transfer, to the positively charged object, will combine them. So positively charged will attract, or will pull the negatively charged object. Okay, so not only can electric charge exist on an object, but it can also move through an object. Okay, so there's no N here. Sorry, there's no D here. Okay, so not only an electric charge exists on an object, but it can also move through an object. So substances that readily conduct electric charge are called electrical conductors, and materials that conduct electric charge poorly are called electrical insulators. Now, to compare the two, conductors versus insulators. So we have here the basic concept between the two. Insulators are poor conductors. They do not allow heat and electricity to flow through them very well. Insulators has examples like rubber, woods, glass, etc. And for conductors, they allow both heat and electricity to flow very well through them. Example of conductors like metals like silver, gold, copper, iron, and so on. So air is a poor conductor. So this is where we talk about wireless communications class, because the transmission of signal is through air, and we know that air is a poor conductor. So that is why when they tell you in cold weather to wear layers of clothing so that your body heats gets trapped in between the layers and it doesn't conduct your body heat away as quickly compared to just a single layer. Okay, so remember here, air is a poor conductor. So as you have learned, no, in our previous discussion, we in wireless communication we use air, no, to transmit our information, or we transmit the information via free space via air. So that's why the concept discussed here is very important to understand. Know how the signal is being transferred from one point to another. Okay, so the basic concept here is about like charging, no? Charging by contact and induction. So this is an example of charging by contact. So you see here, this one touches this object. So this is a metal sphere. This is an insulated stand. Okay, so this is an example of charging by contact. Okay, so this part, the rod contacted this metal sphere, thus the charge is the negatively charged particle here is transferred through this metal sphere. Okay, so another way of charging is by induction, no? Charging by contact and by induction. So a while ago we have seen the charging by contact. So now we have here by induction. Okay, so you see here that the rod is away, no? It's not touching the metal sphere. Okay, so we have here an illustration that we have a grounding wire connection to the ground, right? So what happens is that the electrons transferred to the it leave, and what is left is only this one. So if it is lacking, if there are a lot of holes here or positive charge, so the electrons will be transferred here, so leaving only this. Okay, so this is an example of charging by induction. So another scenario here is that so we have here the passively charged, passively surface charge, positive charge is a negative charge, so this is a plastic. We have here an ebonite rod. So the negatively charged rod induced is the negatively charged induces a slight positive surface charge on the plastic. So the result of this is that it will induce a slight positive surface charge on the plastic. Okay, so this is an example of charging by induction. Charging by contact and induction. Okay, so here comes the Coulomb's law. So listen carefully, because we have here examples of how we can calculate charges, the forces, and so on and so forth. Now, here's an illustration. We have here positively charged here, and then this is positive, and you have negative charge here. So if they are opposite charges, so they attract. So you see the direction of the force. The force going to Q2, and from Q2, force going to Q1. So our sign convention here, if the force going to the right, so we have a positive force, and going to the left, negative force. Okay, so they're separated a distance equal to r. All right, or this is just equivalent to something like this. If the charges are both positive, so you see here the direction of the arrow, so they repel, no? They repel, they're not attracting each other, they repel. So there's a force going to the left, so this is a negative also, no? Like this one, going to the left, negative. And the other one, positive. Of course, it will repel from this, so it will go away from this, go in this direction to the right. So we have here the force which is positive, like this one here, is going to the right also, so that's positive. And they're separated also by this distance r. All right, so remember this concept, class, and you have to understand this setup so that you will understand our calculation, how to do it. Okay, so from the Coulomb's law, we have here the magnitude of electrostatic force. So remember, electrostatic force, the magnitude, how strong is the electromagnetic or electrostatic force exerted by one point charge on another point charge is directly proportional to the magnitude of charges, directly proportional, okay, directly proportional um, of the charges and inversely proportional to the square of the distance, square of the distance inversely. So that's why here in the formula we have F, that is the electrostatic force, is equal to, because we talk about proportionality, class, so to change our expression from proportionality to equality, so we have to introduce a constant k. So the constant k here is equal to 1 divided by 4 pi epsilon sub 0. So epsilon sub 0 is equal to, this is a constant, class, that we are going to use. So this is a permittivity. So that is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. So that is the value of our epsilon. Okay, so this is the electrostatic force. So remember this. This is a very important formula, class, in our discussion about electric field. Okay, so example here, we have a model of a hydrogen atom. In the Bohr model of hydrogen atom, so remember this hydrogen atom, the electron is in orbit about the nuclear proton at the nucleus of, okay, this nucleus diameter, that is 5.29 times 10 to the minus 11 meter. Determine the speed of electron. So we're talking of speed here, speed of electron, assuming the orbit to be circular. So to calculate this, so we have to make use of this formula, class. Electrostatic force is equal to the product of the absolute value of the charges multiplied by the constant, which is 1 over 4 pi times epsilon sub 0, divided by the square of the distance between these two charges. Okay, so using the formula, so we're given here, this is the illustration class of the problem, the Bohr model. So we have here orbit to be circular. Okay, so the orbit is circular. Okay, so this is the radius, this is the direction, the velocity of the electrons as it orbits, no, in the circular fashion. Okay, so using this formula, F electrostatic force, F equal to K times the product of the absolute value of Q1 and Q2. These are the two charges, and the distance divided by the distance, the square of the distance that separates them. Okay, so this is the constant class when you calculate, no? When you have this is, so our key here, our key is equal to, as shown in the previous slide, this is 1 times 4 pi, 4 pi times epsilon sub 0. So this is the permittivity class, and you have this number. This is given a while ago, so this is given. When you substitute it here, so the value of that is this one, 8.85 times 10 to the minus 12 c squared divided by n, or per Newton meter squared. So 8.85, right? This is 8.85 times 10 to the minus 12. Okay, so when you substitute this one here, so the unit here is coulomb squared per Newton meter squared. Okay, so when you substitute this value here, this one, in this, because our key here is this one. So once you substitute this, you will obtain this one. You will get this. So this is the result, no? This is the result. Okay, this is the result after substituting this into this k1 over 4 pi times this value. So you will get this. Okay, then multiplied by, this is given the problem, the charge. Right, so we have here 1.60 times 10 to the so where is this number? So that is the value 4. If you look at the previous discussion, so we have here our A. So this is A 1.60 times 10 to the minus 19. Okay, so this is the value of E. So this one multiplied by this is the charge, no? The charge electron that is in coulombs. So this one can be, the product of this is equal to the value of E. Okay, as shown in the first initial slides class. Okay, so this is the value of E. So divided by the distance between them. Okay, so squaring the distance, so we get this 8.22 times 10 to the minus 8. Okay, so this is, we have here the positive electron, negative electron. So it goes in this direction, the velocity. So we have, after calculating the F here, so we have to make use of this formula, no, from I think this is from physics, and you can also see this one in engineering mechanics, that the force, this force here, the electrostatic force, is equal to the product of the mass times the acceleration. Okay, mass times the acceleration, or this is also equivalent to m, the same m, but our a here is just the ratio of the square of velocity divided by r. R is this r here, the distance between this charge and this charge. Okay. Okay, so this one is the radius, the separation between these two electrons, the positively charged electrons and the negatively charged electron. Okay, so substituting. So from here, F already calculated. So this is our F. So we got this F here. Then substitute it in this equation, but make use of this. So you can have F equal to mv squared divided by r, right? Then cross multiply r, divide by m. So you have therefore v squared. V squared equal to f times r. So you cross multiply r. So you have f times r, then divided by m. Okay, so divided by m. Then after that, take square root on both sides, so you get this one. Okay, so you have all the information that you need. So you have f, okay, this one, substitute. Then you have r, the radius, this one, this is also given. This is the one. Then divided by m, the mass. So that is 9.11 times 10 to the minus 31 kilograms. So that is the mass of. If you look at from our previous slides, okay, so this is the mass of the electron, which is 9.11 times 10 to the minus 31. So we make use of that value and substitute it here in our problem. Okay, so after evaluating, so you have here the result 2.18 times 10 to the minus 6 meter per second. So that is the velocity. Now, as mentioned in the problem, it says determine the speed of the electron, speed or velocity. So the speed is equal to 2.18 times 10 to the 6 meters per second. All right. Okay, so another example. This is our fourth example. 3 charges on a line. So determine the magnitude and direction of net force on Q1. So this is our Q1 here. Okay, so this one. So first you have to translate this into a free body diagram. So the equivalent diagram from this presentation. Okay, so as you say here, you have Q3 equal to this charge, negative. So it means it goes in this direction. Then you have Q2, that is negative also, microcoulomb, and Q1 is positive microcoulomb. So they are all in microcoulomb. So just find the net, the net or the free diagram of this. So 3, meaning difference if you consider 1 to 3, meaning if you consider the force from Q1 to Q3. So we have the force. So the arrow indicates plus above, it means it's a vectorial force from 1 to 3. Okay, and the force from 1 to 2. Okay, so in this direction. So this is our F sub 1 to 2. Okay, so again there's a bar here, so to indicate that this is a vectorial force. So this is 3. So 3 combined with this one, so 3 minus 4. So we have minus. So it means the direction would be to the left. So remaining, so the value here is F12. So going in this direction because minus 4 is greater than this one. So it goes on this direction. Then F13. So F13. So we have here 3, then minus 7. Okay, so F13. So there's a 4, no? For the difference here, the difference is 1. So we just make it shorter, no? Just to indicate that their difference is just 1. The magnitude is just this much. If you look at here, the magnitude is 4. The difference is minus 4. So take that absolute value. Okay, so we have, okay. So here we have, it means that this is greater than this one. So the tendency is that more force is going to tends to go to the right, because it follows the direction of this. All right, so don't be confused, class, why we put the arrow here. We're just indicating that the difference, no, the difference between this and this one. So it tends to be, since the negative is on the left side, all right. So the overall result will be on this direction also. But this is how much we're talking of the magnitude here, class. Okay, so this is much one microcoulomb, the difference. But here the difference is 4 microcoulomb. So you have here 1, 2, 3. This is equivalent to 1, 2, 3. So about three times or 4 times this one. Okay, so this is now the free diagram of this illustration above. So now we are going to in terms of magnitude, no? Magnitude. So in terms of direction, so we can say that so this is the calculation class. So we are given the distance, this distance and this distance, so we can calculate for the forces, electrostatic force. So using the formula, we have K, Q1, Q2, absolute value, the product of them, then divided by the separation between them. So in this case, if you consider 1, 2, for 1, 2, so this is the separation between them. So r squared here, our r is 0.2, so this one. And then k is the result, no, the same calculation, k is equal to 1 over 4 pi times epsilon, where epsilon is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Okay, so when you calculate that one, we got this immediately. Okay, so you just use this class as a constant immediately so that you won't show the value for k anymore, except for the overall calculations that consider the 4 and also the pi and also the epsilon sub 0. All right, so we have here charge Q1, which is this one. Okay, that's given the problem here. And then charge of Q2 is this one. Right, so since absolute value, so don't take the sign of this. Okay, and divided by, you square the radius, I mean the distance between Q1 and Q2, Q sub 1 and Q sub 2. And we get here 2.7 Newton. And similarly for 1, 3, okay, so same constant as this, same K, and then 1, 3, so Q1, that is still 3 times 10 to the minus 6 coulomb. Then our Q3 is 7 times 10 to the minus 6 microcoulomb. So you don't need to carry the sign, because as you can see in the formula, this is absolute value. Absolute meaning if that is negative, so you take the positive. If that is positive, that is still positive. Okay, so we got here 8.4 newtons. Then we have F, no, the resultant or the magnitude, no, of this is just the sum. No, the resultant force is just the sum. The resultant force, the total force, that is the vectorial force that considers these two. So it's just the sum. No, we have F sub 1 2 plus F sub 1 3. And take note that our F sub 1 2 is going on the left direction. So this time class we have to consider the sign. Okay, so we'll consider the sign. So since it's going to the left, so we have here the negative sign, plus 8.4. 8.4, this is going to the right, so that's why we have positive 8.4. So combining the two, so we have the resultant force equal to 5.7 Newton. Alright, so this is the electrostatic force. Okay, you just sum up and then this time consider the sign. Going to the left, uh, negative, going to the right, positive. So we got here the result plus 5.7 Newton. Okay, so we're asked the direction. So now you can say that plus 5.7 Newton to the right, going to the right. You can write this one. This is one option. Okay, so you indicate the direction, it's going to the right, or you just say plus 5.7 Newton, and then you may put something like this, arrow going to the right. Okay, next example is you have here three charges. Q1 is 4 microcoulomb, Q2 is minus 6 microcoulomb, and Q3 is negative 5 microcoulomb. These two charges, Q1 and Q3, are on the same line, but the Q2 is located a certain angle from with reference to this position of Q1 and Q3, that is 73 degrees, and with the distance between Q1 and Q2 as 0.15 meters, and this one is 0.1 meters. Okay, so here's the free body diagram of this illustration here. So this is the free body diagram, and to solve for F, so we have to calculate the magnitude of the resultant. So you have to solve for F12, F13, then after that you add this vector forces vectorially. Okay, so the for this one, this is our force from 1 to 2, so you have to take the vertical component of that, so that is vertical, so you use the sign. If you have this we can form here a triangle. Okay, so this is 73 degrees. So to get this this one, which is equivalent to this one here, it's just the vertical component of this. Okay, so the vertical component, or you just look at this one, class. So this one is just the same as this. Okay, so if you want to solve this vertical part of this picture, so you just use sine sine of the given angle. Sine of the given angle, which is 73. So assuming this is our y, the y component, no? So sine 73 is just y divided by the hypotenuse, opposite over hypotenuse. So what is our hypotenuse? That is our force. No? This is our force from 1 to 3. So vertical force from, sorry, 1 to 2. Okay, so this is a vectorial force. So therefore, this is divided by F12. Okay, so you can solve for y. So y therefore is equal to the product of F12 F sub 12 and multiplied by sine of 73 degrees. Okay, so this is it. This is the y component. Now for the x component, so you can have here x. So in this case, you use cosine of the same angle, 73 degrees, equal to adjacent. Our adjacent is x over hypotenuse, which is still F12. Okay, so there's a bar here, there's a bar here. Okay, so cross multiplying, so you get x equal to F12 from 1 to 2. Okay, then multiplied by cosine. Now cosine of 73 degrees. Okay, so as you can see here, so this is the horizontal component, this is the vertical component. Alright, so what we're going to do is to solve for this one. Okay, F13, and then we solve for F12, and after that we solve for the resultant force. Okay, so how to do that? Okay, so you just calculate. No? We have so once you get this one, solve for F12, right? How to solve for F12? Use the formula that we just used. F equal to K times Q1 Q2. The absolute value of this. So absolute value of this also, and divided by R squared. Okay, so once you obtain that one class, you just add the two vectorially, and if you look for the magnitude, then you can just take the square root of the square of this one and this one, and you will get this. Okay, so I hope you understood what I am talking about, class. So use this formula, okay, to find this F12. This is our F12 is can be okay. So our F12 can be solved using the formula. So our F12 is here, F sub 1 2. Okay, and then our F sub 1 2 also here. F sub 1 2, this one. Then apart from this, you calculate using this one. So you have to sum up forces class, because you have we have the vertical component, the horizontal component of F12 that can be combined with F13. Okay, they are both on the same directions. All right. Okay, so after that, you will have this the overall result of the horizontal component and also the vertical component. So on this part, there's no, anyway, you will learn later on what I'm talking about after I discuss the next problem. But the technique here is to solve for this F12, and then you solve also for the F13 here using the same formula. Okay, then after that you have a F13 going in this direction to the right, but this one here, you consider the horizontal component of this part to the right also, so that would add. Then we have the vertical component of this one. Okay, but this one has no vertical component, so that is equal to 0. So your vertical component, overall vertical component, is 0 plus this one. Okay, then your horizontal component is F13 plus this, because both of them goes to the right direction. All right, so to get the overall result, so we have here the F, that is the resultant, no, the resultant of all the F here, the forces. Okay, so you'll understand more the details of how this problem could be solved. I will show you another example here to help you understand. But before we go to that, uh, we'll discuss here another concept related to what we have discussed a while ago. Here, calculate the net electrostatic force on charge Q3 due to Q1 and Q2. So the same concept class. So you have to solve for this one. Okay, solve for the force here, and you have the force here, and the good thing about this is because they are perpendicular to each other. Okay, so I think calculation here is simpler. So the same class, use the formula now, same formula, F. So F is equal to K. You can put K here or here, no problem. So Q1 times Q2 divided by R squared. Okay, so use this formula to find the force from Q2 to Q1, or Q1 to Q2, and also from Q2 to Q3, and then combine the horizontal and vertical axis, and you will find the overall, the net electrostatic force. Okay, so for your practice class, do it anyway. The example will be shown, no? If you don't understand how to do it, you will see in our coming example, you will see how to do it. There will be details of our calculations there. Okay, so the positive charge experiences a force which is the vector sum of forces exerted by the charges on the rod and the two spheres. So this charge should have a small magnitude, so it doesn't affect the other charge. Okay, so we have here an illustration. So positive charge experience a force which is a vector sum. So this positive charge here, which is a vector sum of forces exerted by the charge on the rod. Now, by the charge exerted in this rod and the two spheres. So this one, these are the two spheres. So this discharge should have a small magnitude so it doesn't affect other charges. Okay, so here are the sample calculations for test charge. So the positive test charge has magnitude of 3 times 10 to the minus 8 coulomb. Okay, so this charge here, this charge, and experience a force of 6.0 times 10 to the 8 Newton. So this force. So find, letter A, find the force per coulomb. So for force per coulomb that the test charge experiences. Then predict the force that a charge of this much, 12 times 10 to the minus 8 coulomb, would experience if it replaced the test charge. Okay, so here's the solution. We have the ratio, the force, ratio of the force and the charge is equal to, so we're given this. So we got here the force, no? The force in coulomb, the force per coulomb. So Newton per coulomb. Okay, and for B, the charge predict the force that a charge of this much, 12 times 10 to the minus 8, would experience if it replaced the discharge, if this will be replaced. Okay, so assuming what this one is talking about is if we replaced this one with the result, which is this one. So predict the force that a charge of positive 12 times 10 to minus 8 would experience if it replaced by, or if it replaced the discharge. So F, so we have here F. Okay, so replace this. This is our discharge, which is originally 3. We have to replace it with this one. Okay, so this one is replaced with this one, and then the force that will be experienced. So you just cross multiply this one. Okay, so this are our force. Okay, so this is the force per coulomb. Okay, multiplied by the force per coulomb multiplied by this charge, but this is replaced by this. Okay, and this gives us 24 times 10 to the minus 8 Newton. Okay, so what happens is that the force increases, or has increased. All right. So I hope you have understood the calculation class, basic calculation on the class. Now we have here the definition of electric field. So this is our main topic class. So the previous topics that we've discussed, just the continuation. So the electric field that exists at a point in the electrostatic force experienced by small test charge placed at that point divided by the charge itself. So it's given by this electric field. Okay, so electric field equal to the force divided by the charge. Okay, so this is the formula for the electric field. So SI units of electric field is in Newton per coulomb. So Newton per coulomb. So this is electric field. Okay, this is an example of a positive charge Q sub 0 experience an electrostatic force F due to the surrounding charges on the ebonite rod and the two spheres. Okay, so we have a charge here. So because of these charges of the ebonite rod and also this sphere, two spheres will affect this charge. So this is a positive charge Q sub 0 will be affected by because of these charges. So it is the surrounding charges that create the electric field. So remember, it is the surrounding. So this electric field here that will be developed will be due to these charges around. So the surrounding charges that create the electric field at a given point. It is the surrounding charges that create the electric field. It is the surrounding charges that create the electric field at a given point, like something like this. So we have here the charge here at positive 18 times 10 to the minus 8 coulombs. It is affected by this, so it has its electrostatic force, and because of this, so there will be electric field that affects this charge. Okay, or it can be something like this. We have perhaps because this is negative. Okay, so the electrostatic force is going down. Here, this is positive. So this electrostatic force going up. So this is going down. So it can be, in this scenario, possible scenarios, it can be going in the same direction or it can be in opposite direction depending on the charge of the point. Okay, so another example 7. So an electric field leads to a force. So the charge on two metal spheres and the ebonite rod create an electric field at the spot indicated, as this one indicated here. The field has a magnitude of 2 Newton per coulomb. Okay, so the field has a magnitude of 2 Newton per coulomb. Determine the force on the charges in A and in B. Determine the force on the charges in A and in B. So as shown in this figure, the electric field E that exists in a given spot can exert a variety of forces. So the force exerted depends on the magnitude and sign of the charge placed at that point. So for illustration A, so the force on a positive charge points in the same direction as E. The force on a positive charge points in the same direction as E, while B, so in this illustration, the force on a negative charge points opposite to E. Okay, so this is opposite to E. So this is negative. So this one positive. So the force for A, so the force on a positive charge points in the same direction as E. While B, this is our A class. This is our A, this is our B. And B, the forces on a negative charge points opposite to E. So our E is going this direction, our F is going in the opposite direction. Alright, so the calculation is something like this. So from the formula, E is equal to F over Q, or we can solve for F equal to Q sub 0, the charge multiplied by the electric field. So equal to, okay, so this is our electric coulomb, no? from the formula. So from this formula we have here Newton per coulomb. So our electric field is Newton per coulomb. Okay, so Newton per coulomb. So this is our E, 2 Newton per coulomb. This is our A, multiplied by the charge, which is 18 times 10 to the minus 8. So therefore we have 36 times 10 to the minus 8 Newton as the force for this illustration for A. And for B, so same calculation class, just substitute. So you start with the electric field first, okay, 2 Newton per coulomb, and multiplied by the charge negative. Now that is negative, this one, 24 times 10 to the minus 8. And we got 48 times 10 to the minus 8 Newton. Alright, so another illustration is something like this. We have here particle with a charge of A. This is our charge A, charge B. So positively charged, positively charged. And this is our point P. Okay, and we are given here the electric field along A is going to the right, and along B going to the, or going down. Okay, so electric fields from different sources add as vectors. Electric fields. So this is our illustration class. So electric field of A and electric field of B. And we have here the resultant of the electric field. So this is a vector, so you just add the vectors. So vectors AA plus the vectors EB. So that gives us E, electric field E, the resultant. So to help you understand class, for vectors, so just to recall what we have in the mechanics, impulse and momentum solution. So we have here a scenario. Force is something like this. Okay, so you solve for the x component, then we have to solve the y component, and after that you get this 2. This is the force along the x-axis, or this is the x component, and this is the force along the y-axis, or the vertical component. So you just simply add them, f of x, so this one, then you just put I, so to indicate that this is for the x component, then f sub y, this one, and then you put j, so it indicates that this is for the vertical component, or equal to f. Now our f here has no more symbol for a vector, so we have f is equal to 97.5 pounds, so that is in terms of pounds. So in this case, how to get this one? So you just take the square root, so f here is calculated as from vector, the square root of the sum of the squares, meaning we have 89, you square this, then plus 39, 39.9, then squaring this one also. So after that you get the 97.5. Okay, so this is the result. So the result here, will be this one. Okay, so try to calculate. Now, this is just an example class. I'm just showing you this just to help you recall, no? How to calculate the force, vectorial force. So this is a lesson in mechanics. Now to continue. So in this illustration in figure 18-17, so it shows two charged objects A and B. It contributes as follows to the net electric field at point P. Now this is a point P. Now this point here, this point. Electric field of this object is equal to 3 Newton per coulomb directed to the right. And for B, electric field of B, that is equal to 2 Newton per coulomb, and that is directed down. Thus, EA and AB, A sub E, electric field of object A and electric field of object B. This is the electric field of object A, meaning this object, and the electric field of object B, so this object, are perpendicular. They are perpendicular, meaning they are separated 90 degrees. So what is the net electric field at P? So what is the net electric field at P? Okay, so here's the reasoning class. So the electric field contributions A and AB, which comes from the two charges distribution, are added vectorially to obtain the net field E. So this is what we call net field. So the symbol is this, net field at point P. So reasoning, the net electric field, which is this one, is the vector sum. This is the vector sum of the electric field of this object A and the electric field of this object B, and that is equal to the sum, vectorial sum, as in the illustration, shown in this illustration. So electric field of object A and electric field of object B are perpendicular. So E, the electric field, the net electric field E, is the diagonal. This is the diagonal of the rectangle shown in the drawing. Okay. Thus, we can use the Pythagorean theorem, because this is triangular. So we can use the Pythagorean theorem to find the magnitude of this net electric field, and trigonometry to find the direction, meaning the angle. So when we speak of direction, so we are referring to an angle. So in this case, an angle theta. This angle here, this angle. So the solution is something like this, as I have shown you in previous slide, as I mentioned about engineering mechanics, that slide, that inserted slide. So to find the magnitude, the magnitude of E is just the square root of the sum of the squares of the electric field of object A and also the square of the electric field of B, object B. So substituting, so we get here 3.61 Newton per coulomb. So that is the net electric field. That is the resultant, not the resultant field. Okay, so the direction of the electric field is given by the angle in the drawing. So from this, opposite over hypotenuse. So the opposite here, if this is EB, this is also same. This is also EB here. Okay, so to solve for this angle, you can use tangent. So we have from trigonometry, we have tangent of the angle, or tangent of the angle theta is equal to opposite. So this is our theta, opposite is E sub B, and divided by so this is divided by E sub A. So from here, just take inverse or arc tangent, so you get theta. So theta is just the arc tangent of arc tangent. There's a negative here, means inverse tangent of electric field at B divided by the electric field at A. Okay, so that's why you have here in the solution. Okay, so we have theta is equal to this, substituting the value, so you get 33.7 degrees. Alright, so that is just taken from this illustration, trigonometry. Okay, so another problem, the electric field of a point charge. You have here the isolated point charge of, what is given, isolated charge Q, given as 15 microcoulomb, and the discharge, so this is discharge of 0.20 meter. The discharge is 0.20 meter to the right, and has a charge of, so this is the discharge, Q sub 0 equal to 8 microcoulomb. Okay, so shown in this illustration, you have here, this is our Q sub 0, and we have here the positive charge, negative charge. Okay, so if this is positive charge, right? So what will happen? They will repel each other. Then using this formula, electric field, which is a vector equal to the electrostatic force, which is also a vector, divided by the charge, which is what we call the discharge. Okay, so from the formula, F equal to the constant K, which is equal to 8.85 times 10 to the minus 12 coulomb square per meter, Newton meter squared. Okay, so using this formula, so at A, at A, so at location, so A, we have here B, C, so at location P, here this is our location P, this is our location P. A positive discharge Q sub 0 experience a repulsive force, because this is positive, so the repulsive force is going to in this direction. Naturally, this is also go into this direction. Okay, so this is due to the positive point charge Q. That's why it goes in this direction. Then at B, at point B with reference to, meaning at P with this picture, B. Okay, so electric field is directed to the right. Okay, so directed to the right. And C, if the charge Q were negative, so this is negative rather than positive, so the electric field would have the same magnitude in B, but would point to the left, like this. Okay, so what will happen is, so we have here the illustration using the formula. This is a constant, 8.99 times 10 to the minus 9, then multiplied by what is Q. So as indicated here, our Q is 15 and our Q sub 0 is 18, so micro coulomb. Sorry, that is 8 micro coulomb. Okay, so actually there's no problem because you can interchange the position of this. So no problem. This is just multiplication. Alright, then the separation between them, that is R. So as mentioned in the problem, this charge is into 0.20 meter to the right and has a charge of this. So to the right. Okay, so after substituting, this is given, right? This is given. This is calculated, but based on the standard value for epsilon sub 0. So after substituting, we get 27 Newton. Okay, so to solve for E, so we just use this formula for E. Okay, so we use this formula. Okay, so E is equal to F over the charge, equal to 27. So we get this. Then using for Q sub 0, 8 point times 10 to the minus 6. So where is this coming from? Q sub 0, it's mentioned here in the problem. Okay, so the electric field is equal to 3.4 times 10 to the 6 Newton per coulomb. And take note, class, that we can also manipulate the equation of the electric field. So we're given E equal to F divided by the absolute value of the charge. So in this case, we call it the discharge, discharge Q sub 0. Okay, so equal to, so we know that we know F because we can write this as E equal to, we can write this as E equal to F, right? This can be written as F multiplied by 1 over Q sub 0, right? So this, so this one is just the same as this. This is just the same as this. But we know that F, so we know that F is equal to K multiplied by Q. It can be Q1 or Q2. It can be Q1, Q2. Absolute value of this and absolute value of this, and they are multiplied and then divided by R squared. Okay, so now if we are going to substitute this, in this case we use Q without subscript. So you can use Q That's all right now if you use Q1, just to match with this. Okay, so substitute this here. So what will happen is that you have, when you substitute it here, so you will get this. By the way, this is, you can use Q and Q sub 0. So it doesn't matter class, this is just a subscript. You substitute this, so you have Q sub 0 here, you have Q sub 0 there, the numerator, so when you divide it, that's equal to 1. So therefore, the point charge Q, we have the point charge Q equal to this. So another formula. Okay, so that is derived from these two formulas. Okay, so we'll make use of this formula in our coming examples. So another example here, the electric field from separate charges may cancel. Two positive point charges. The electric field from separate charges may cancel. So if you have two positive point charges like this one, example, two positive point charge Q1 equal to this. So this is our Q1, positive 16 microcoulomb, and Q2 equal to positive 4 microcoulomb, are separated in a vacuum at a distance of 3 meters. So distance of 3 meters. Now find the spot on the line between the charges where the electric field is 0. The net electric field is equal to 0. So meaning A is equal to 0. And you are asked to find the spot. Where is the spot? Meaning distance. If you, like for example, you put the spot here at this point, point P, that is our point P. Okay, so this is, because this is given. Okay, this is given, so you can let this distance from Q1 as D, or it can also be that you put D here, no problem, or vice versa, no, dito on D, and then the difference of 30 and D here, so meaning what is left here, so this distance, simply this distance, which is 3, right? This is just 3.0 minus D. Okay, so this is now the distance between this spot and Q2. Alright, so using that relationship, then we can solve for the location. Actually, we are asked to solve for D here. That is the distance D. Okay, so E equal to E times the charge divided by R squared. It says that electric field, the net electric field is 0. Okay, so this electric field, net electric field will become 0 only. 0 F and only F. F and only F. F and only F. E1 is equal to E2. Meaning the magnitude of E1 and E2 are equal. So equal and in opposite direction. So in this case, opposite direction. So they will just cancel. Alright. So substituting, we have this using this formula. So this is our E1. Okay, on this part. Sorry. The subscript should be E2. Okay, so substituting. So this is our A1 part and this is our A2. So substituting, we have K here, the constant. 6 times 10 to the minus 6. So this is given a problem for Q1. Okay, so Q1 here, 16 micro coulomb positive. And the other side we have 4 micro coulomb also. So K, so the K here, divide K or, yes, divide K both sides, so this will cancel out. Alright, so after that you cross multiply this. You cross multiply this part here, then cross multiply this one. So you get this one. Okay, then evaluating. So distribute and multiply. Okay, so distribute and multiply, and also this. So what will happen after that? You combine with this. So you have 4 times 3, that is 12, right? 12 meter. Then minus 4. Sorry, you cannot do that because that is square. We can't do it because this is square, so you have to expand first. No? You have to expand first. Another way is you have to combine all these in one side and put 0 on the other side. Okay, so just perform the operation, algebraic operation class. This is algebra. This is algebra. So you have you can solve D here. So one way is to expand this one. You use the binomial expansion. Okay, so you can use this binomial expansion U plus V squared. Okay, so you use this expansion from algebra. So you have U squared, okay, for the first term, plus twice the product of the first and second term, so 2UV, then plus the square of the second term, which is V squared. So you expand, meaning you have to expand this part here, and after that you distribute and multiply the 4. Okay, and then combine similar terms. After that, I think you need to factor. Okay, or another way is, I think you can take square root on both sides. Yeah, I think take square root on both sides. So when you take square root on both sides, you have, okay, so let's say if you take square root on both sides, so you have, we have taking, let us try if we can do it now. Taking taking square root on both sides. You take square root on both sides, so you have square root of this is 2, and you have this one 3 minus d. Okay, 3 minus d. Just leave the unit class equal to d. Okay, and then so this will be, you distribute and multiply. So you have 6 minus 6 minus 2d equals d. Okay, and then after that you transpose this to other side. So this becomes, I continue it here. So this becomes 6 equal to, when you transpose 2d, this is negative 2d, so becomes positive 2d, right? So positive 2d plus d is 3d. Okay, so 3d. Okay, divide both sides by 3. So that's why you have d is equal to So don't forget to write the unit. Okay, so D is 2 meters. Okay, so no need to do this class. It would make, you can do this also, but it's better to do it this way. You just take square root on both sides. Okay, so you got D equal to 2 meters, positive 2 meters. So distance is always positive. So we have here another conceptual example 12, symmetry and electric field. So point charges are fixes to the corners of rectangle in two different ways. So the charges have the same magnitudes but different signs. So consider the net electric field. Now consider the net electric field at the center of the rectangle in its case. So which field is stronger? Okay, so we have here the illustration. So we have here the net electric field here at the center. Okay, right, so you can calculate. No, we have here the electric field. So you just do the same calculation class using the same concept. So this one will just, if you look at this, so this will attract, they will repel, and they will repel. So the tendency is this one, something like this. Okay, sorry, they will reflect. Anyway, the point here is, so point charges are fixes, fixes to the corners. So these are the corners in a rectangle in two different ways. Okay, so it can be something like this, plus minus, something like this, plus minus, plus plus, or it can be minus minus, plus plus. Okay, so in this setup we have this result, or if you have this kind of setup, so we have this. So which field is stronger? Okay, so you will know that class when we have this example here. But before we go to that example, let us discuss this first, this concept. So electric field, parallel plate capacitor. So in a parallel plate capacitor, so we have here the positively charged plate. This is a negatively charged plate. So the electric field is perpendicular, perpendicular to these plates. And we have here the area. Okay, so the electric field E here is given with this equation Q divided by epsilon sub 0 multiplied by A. Alright, so that is still taken from the relationship class because your A, so we're talking of area of the plate now. So we know that area, we have area is equal to pi r squared. Okay, so we have area equal to pi r squared. So in our discussion a while ago, because this is we have force, right? Force is equal to Q we have the formula of force. Force is equal to remember in our this one. So we have come up with this equal to K Q over R squared. Okay, Q over R squared. Okay, so with the combination of all this information, so we can derive our A is equal to Q over, because our K, we have our K, we can still remember our K is equal to 1 divided by 4 pi epsilon. Okay, so we have this value of K. So if you're going to replace it here, so what will happen if you substitute, if you have substituted here, and then our A, we have our F here, A. So this is sorry, this is A. Okay, so if we are going to substitute this one here, so what will happen is we have A equal to, instead of K, so write it down. So that would be 1 over 4 pi epsilon, then multiplied by, because we have separated this one, right? We separated this one. So times Q, this is Q plus, divided by R squared. Alright, so now we have change this color to, so we have here pi, okay, we have here pi, and we have R squared. So you know that so you can combine that as, so our expression becomes, so from here, so we have epsilon, sorry, this is electric field, not epsilon. So we have Q, so the numerator here becomes Q over 4 times area, and times epsilon sub 0. Okay, so I think we have some concern here. I forget how to relate with this one. But anyway, this is how this equation is being derived, class. I'm just combining with this. Okay, so this is basically the resulting equation. let's check now. Let's check. Okay, anyway, just have this constant. I cannot resolve this one. Just try to review the other part. Uh, anyway, this turns into this equation. Okay, Q epsilon A. So in our derivation here, we have 4. So I cannot resolve where is this coming from. But anyway, it's just somewhere around. No? Just double check. Um, so here we use this value for our epsilon. Okay, and then for parallel plate capacitor. Okay, so this is okay. So I think perhaps this is the recent class for a parallel plate capacitor. So we have this equation. This is an established equation already, class. That we have the electric field equal to this. So the condition here is that for parallel plate capacitors. Okay, so parallel plate. So uh, okay, and this is equivalent to uh, epsilon divided by, sorry, this is sigma. This is sigma divided by epsilon sub 0, where epsilon sub 0 is the permittivity of phase space. So in this expression, the Greek symbol sigma so denotes the chains per unit area. So in other words, sigma is just Q over A. Okay, so the sigma here, okay, so the sigma here is just the ratio of Q and A. So Q divided by A is just equal to sigma. So this is what is meant by this statement here. And is sometimes called the charge density. Okay, so just remember the term, class. This is called the charge density, except in the region near the edges. So the field has the same value at all places between the plates, and the field does not depend on the distance from the charges, in distinct contrast to the field created by an isolated point charge. So this is the difference, class, now for a point charge and the charge that is discussed in this part. Okay, so remember the basic concept about this electric field in the parallel plate capacitor. Okay, now the other concept is something like this, class. So electric field lines or lines of force provide a map of the electric field in the space surrounding electric charges. Okay, so we have here the positively charged uh, in the middle of this circular uh, setup. Okay, so if this is positive, at this, considering this illustration A, so at any point or at any of the 8 marked spots around a positive charge point charge, so positive point charge, So this is our positive point charge, Q. So a positive test charge would experience a repulsive force. So these are the repulsive force. Now, directed radially outward, so it's going away. It's going away from this center, from the core. And for B, illustration B, you can see that the electric field lines. So now it talks about electric field lines. So electric field lines, you see these are the electric field lines, are directed radially outward from the positive point charge Q. So it's going outside, no? Going away from this. So this is the electric field lines. And the opposite of that is, if this is negative charge, so the field lines, the electric field lines is going to, or going inside, or going directly towards the negatively charged, this Q here. Okay, so electric field lines are always directed away from the positive charge and towards negative charge. Okay, so it goes toward the negative charges. So this is our negative charge, so the electric field lines going towards the negative. Okay, so another illustration here and explanation. Electric field lines always begin on a positive charge. So remember this, huh? Electric field lines always begin on a positive charge. So it means if you look at the arrow, it's directed towards negative. So it starts from positive and goes to the negative. So in this figure, in figure 1825, in the central region of parallel plate capacitor, okay, so in this illustration here, in the central region of the parallel plate capacitor, so this is our plate capacitor and this is the front view, the electric field lines, the electric field lines are parallel and evenly spaced. Now they are evenly spaced, indicating that the electric field there has the same magnitude. So it means they have the same magnitude and direction at all points. Okay, so remember this class, these are very, very important statement. An electric dipole, so an electric dipole consists of two separated point charges. Consists of 2 point charges that have the same magnitude but opposite signs. So same magnitude but opposite signs. Okay, so that's electric dipole. So you can see it here. The number of lines leaving a positive charge or entering the negative charge is proportional, proportional to the magnitude of the charge. So proportional to the magnitude of the charge. So an electric dipole consists of two separated point charges that have the same magnitude but opposite signs. Okay, so please remember this statement, class. Again, this is a very important statement as mentioned a while ago. So repeated it here. So you have to remember this. And electric dipole consists of two separate point charges that have the same magnitude but opposite signs. So in this picture, so the electric field lines of an electric dipole are curved. They are curved and extended from positive to negative charge. So this term, remember, is extended from positive to the negative charge. At any point, such as in point 1, this point here, so this is point 1, these are point 1 and point 2 and point 3. So at any point, such as in 1, 2, or 3, the field created by the dipole is tangent, no? Tangent to the line, tangent to the line through the point, tangent to the line through the point. Okay, this is tangent, this line here. Okay, so here is the opposite, no? In this picture, we have positive, negative. We have two charges here of opposite. We have 2 point charge, or 2 points here with opposite charges. So these are the dipole. But here they have the same. They have the same charge. So the electric field lines for 2 identical positive charges. So this one shows the electric field lines with 2 identical positive point charges. So if the charges were both negative, then direction of the lines would be reversed. So it means it will go, it will reverse. If this is minus minus, if both negative, no? If both negative, so this will be reversed. So now it's going away, right? It's going away. You see it going away, repel each other. So reverse meaning it means it's still going away, but it's in a reverse direction. Now we have here conceptual example 13, drawing electric field lines. So there are 3 things wrong. No? There are 3 things wrong in this illustration class for A, no? For this illustration A. Meaning this illustration here, there's something wrong. No, there's something wrong with this illustration. So let us see if you can still remember the concept and apply it here. So reasoning and solution. So one aspect of figure 18-28A, this picture, that is incorrect is that electric field lines cross at point P. So electric field lines will not cross. So this one is already wrong. So that's the first wrong. So field lines can never cross. So remember that field lines can never cross. Okay, and here's why. An electric charge placed at P, placed at this point P, experiences a single net force, just a single net force. So that single net force is due to the presence of the other charges. So what are the other charges? We have this charge, this charge, this charge, and this charge. All right. So these are the other charges in its environment. So therefore, there is only one value for the electric field, which is the force per unit charge at that point. So if 2 field lines intersected, so there would be 2 electric field at the point of intersection. So one associated with each line. Since there can be only one value of the electric field at any point, there can be only one value of electric field at any point. So remember this. So there can be only one value of electric field at any point. So there can be only one electric field passing through that point. Okay? So because of that reason, so there can be only one. So there is only one electric field passing through that point. Okay, so that's the problem class. So to continue, so another mistake, this is another mistake of this illustration in this figure. So in figure A, so this is our figure A. Okay, is the number of electric field lines that end on the negative charge or negative charges. So remember that the number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. So the negative 2q, meaning this one here, or this one, The negative 2q charge has half of the magnitude of this 4q, meaning this 4q, half of this. Therefore, since 8 lines leave positive 4q, so 8 lines, we have 4 going this direction, 5, 6, 7, 8. So there are 4, there are 8. Now there are 8 lines leave at positive 4q charge. So 4 of them, meaning 1/2 of them, must enter 2q. So must enter 2q. So this is okay. This is the right way of doing it. Of the remaining 4 lines, that leaves the positive charge to enter each of the negative q charge. So that's why it's really wrong. So in other words, so since 8 total number of lines, so we have 4, half of it will go to 2. So 4 going to 2, and then 2 going to negative q, and the other negative q. So this is the correct. This is wrong. Okay. All right. So another concept is something like this: the electric field inside a conductor shield. So the electric field inside a conductor shielding. So this is for shielding class now. The electric field inside a conductor. This is what we call shielding. So at equilibrium under electrostatic conditions, any excess charge reside on the surface of a conductor. So it will just stay inside. No? At equilibrium under electrostatic condition, the electric field is 0. So remember this, electric field is 0. That is at equilibrium, at this condition, equilibrium. The conductor shields any charge within it from electric field created outside the conductor. Okay, so remember these 3 concepts. So here's the sample of shielding. Okay, so we have here okay, so it means that the electric field just outside the surface of the conductor is perpendicular to the surface at equilibrium, so under electrostatic conditions. So 90 degrees, meaning here this is 90 degrees class. This is the it is enlarged now. This part here is enlarged, and you can see it here. So it means this line here is perpendicular, meaning this is 90 degrees. 90 degrees with respect to this circular part here. Okay, so that's 90 degrees, so perpendicular. So this is cylindrical conductor class now. This is just the front view of the cylindrical conductor. Okay, or sorry, this is the end view. And here we have the electric field is equal to 0. So inside the cavity, the electric field is equal to 0. So this is solid, this is open. So this is the cavity. So the electric field here is equal to 0. Okay, so another concept. A charge is suspended, It's suspended at the center. Here is the center of a hollow. So this is a hollow conductor. Electrically neutral spherical conductor. This is spherical conductor. Show that this charge induces a charge of negative q on the interior surface and a charge of positive on the exterior surface of the conductor. So in this illustration class, a positive charge q is suspended at the center, okay, of a hollow spherical conductor that is electrically neutral. So induced charges appear on the inner and outer surfaces of the conductor. So you can see here the electric field within the conductor itself is 0. The electric field within the conductor itself is 0. Alright, so I hope you get the concept class of this illustration here. Alright, so we have here a very good example that applies all the concept that we have learned so far. So charge Q1, equal to this. Okay, so I think class, I have to cut this video at this moment because it's already so long. I will continue it in the other video. Alright, so thank you very much for patiently watching this lecture, and to see on the continuation of this video, I'll prepare another one. Okay, so thank you very much, and hope to see you again in the next video. Bye.